And then I'll tell you about sweet, sweet revenge. So you can do sum of torques. And the goal here is that if this is a system in equilibrium, the sum of torques would equal 0. So that means that the positive counterclockwise torque, so the torque for Ms. Nick, added to the negative clockwise torque would give you 0. Another way to approach this is to move the equal sign and to do this. Now that's the way I usually solve these problems. In my mind, it sort of feels like the equal sign is where the pivot point is. So kind of like when we did collision problems, this sort of matches the teeter-totter. So the counterclockwise torque from Ms. Nick goes on one side of the equation, then the equal sign is the pivot point, and the clockwise torque is on the other. I know that's not reality, but it just seems to make a little more sense. I have no problem with you doing sum of torques and setting it equal to 0, or having your equilibrium be kind of like the teeter-totter itself. So let's put some numbers in this. I'm going to use this method, but you can use the top one. So torque is force times lever arm. Everything is already perpendicular here, so we don't have to use any trig, which we're going to do in just a minute. So the force on my side of the teeter-totter is 70 pounds. That's the pound symbol. And the distance to the pivot point is 8 feet. The clockwise torque from Larry, 150 pounds, 40 pounds, that's right, thank you. I think you probably weighed more than 150, times 4 feet. And when you multiply those, you get to say, I don't know, whatever that is, 320, right? So 320 foot-pounds. Okay. So that's how we solve teeter-totter problems.